Alright, so today's lesson is 10.2, and it's on page 445 if you're Stuart Calculus there. We have just talked about finding areas, an area under a curve, and if we look back to some previous things that we've done here, we talked about that as being the antiderivative, right? Evaluated at the right boundary minus the antiderivative evaluated at the left boundary. And so we talked about that and established that the area under a curve could be represented and found by doing this. So it includes taking the antiderivative and evaluating that antiderivative at the 2 points. So I'm just going to skip ahead here to the notes from 10.2. This is an example in your book. This is not where the textbook starts. This is where I want to start, because instead of just telling you, hey, this is the shortcut, here's the formula, this is what you do, over and done, just go ahead and practice some questions. I want you to see, and it's not going to take too long here, but I want you to see why the area between curves is fairly simple, but I want to show you graphically and sort of explain. So if we're talking about, in this example here, if we're talking about finding this region R, okay, so it's the shaded region here, you can see where it's bounded, okay, at these points and along these lines, right? There you go. And so this is the shaded region here, and the example is on page 456 there. So if this is what we're trying to find, it probably is not too difficult for you to see this larger area. If we just take a look at this one function, right? This area right here, all the way down to the x-axis, which we studied in 10.1, that is the value of the antiderivative of this function, right here, evaluated at 3, and then subtracting the antiderivative of the function evaluated at 1. Right? So we know that the antiderivative, if 3 is our right bound, okay, the area function is the antiderivative of the function evaluated at 3 minus the antiderivative of the function evaluated at 1. That gives us the entire area here. Established? Yes? Agreed? Okay? That's what we just looked at, 10.1. Now, if we want to find this shaded region, you can consider that this region right here in yellow is a separate area that we would indeed want to subtract from the original area. And so this is the function y equals x, and so the antiderivative of that function, evaluated at 3, would be the area function, would be the antiderivative evaluated at 3 minus the antiderivative evaluated at 1, and that would give us that yellow area there. And so what we see is that if we find this area here, and we subtract this area, we're going to get the area in question. Okay? And so, because really we're doing the exact same thing, we're using, see this right boundary, that's the exact same point, and this boundary is the exact same point. Okay, what we can do is we can kind of see this, because we're doing the same sort of thing here, okay, we can back it up to here, which is really what we're doing, right? For function 1 and function 2, we're taking the difference here. But we can also back it up a step further, and I'm going to first of all do this, but then I'm going to show you another method and why it works. So let's just go ahead and do this, and we'll come up with a value for the area of R. Okay? So over here, what's the antiderivative of this function? It is 1/3 x cubed, thank you, plus x, right? And then if we were talking about the general antiderivative, we have to add c. We don't have to add c here, right? Because we're talking about area under a curve. So don't add c there, you don't have to. Under here, what's the antiderivative of this one? I can hardly even see my cursor here. Right, okay, the antiderivative here, or the capital F I should say. Can you guys see that? No, not bad. The antiderivative here of x is what? Yes, 1/2 x squared. Okay, very good. So let's go back over here. going to make a little bit of space here. See what that does. Okay, that's good. So if we're back to, can you guys see this pink all right? Okay, so the area here, that is this whole big section right here, right, is the antiderivative evaluated at 3, so we said that was 1/3 3 cubed minus 3, and then subtracting the antiderivative evaluated at 1, or 1/3 1 cubed minus 1. Does that look good so far? One-third of 27 is 9 minus 3 minus 1/3 plus 1. So that's 6, 7 minus 1/3. Oh, sorry, what? Oh, I got a minus here. Thank you. Yes, thank you. That's a plus, and that's a minus. Thank you. Good job for noticing that. So that is a plus because we got the plus here. Thank you. So that's a 9 plus 3, which is 12. Right? Minus 1/3 minus 1. And so that's going to be 11 minus 1/3, which is 33 over 3. And that's going to be 32 over 3. So that's the large area. Let's take a look at this yellow area down here now, the smaller area. And the antiderivative is right down there. And so the area here for this one would be 1/2 3 squared minus 1/2 1 squared. Okay, so that's 9 over 2 minus 1 over 2, that is 4. So our total area of R, okay, so this was R right in here, remember this part there was R. So that's going to be 32 over 3 minus 4, right? So that's 12 over 3, so that's going to be 20 over 3 for an area, okay? 20 over 3. Now that's taking separate areas and subtracting them. Now, as I mentioned before, we can, because we're doing the same sort of thing for each antiderivative here, right? Taking the difference, upper boundary, lower boundary, that sort of thing. We can consider these two area functions and really take the difference of them. If you take the difference, okay, oops, I'm going to just pull that aside for now. Okay, if you take the difference of two area functions, so this is area function 1, right, which was the area underneath the big curve, and subtract the area under the second function, which was this one, to end up with R here. Okay. Really, what we can do is go back even further and say, you know, if we're still taking the antiderivative of both of these functions, why don't we try and subtracting the functions to begin with? So why don't we do this first? Because we're coming from here, from here. Why don't we do this? The first function minus the second function. Why don't we actually do this first and then take the antiderivative of the sum, or the difference here in this case. So that's what we're going to try. We're going to try that, and then I'm going to show you a couple other things that that need to happen. But let's take a look at this first. This is y equals, and what was this, x squared plus 1. This is y equals x. So just for kicks, okay, let's do a function g here. Oops, small g. Let's do small g, which is x squared plus 1 minus x. Okay, because you see how we're subtracting the antiderivatives? Okay, so let's subtract the two functions first and then see what happens. So that Okay, that looks good. You can change it to something a little bit more familiar if you want, like this, but you don't have to. So if we take the antiderivative of this, right, this is going to be what? 1/3 x cubed minus 1/2 x squared plus x. Okay? And, maybe I shouldn't have changed this around, but if I wouldn't have changed it around, it actually would have looked like this. Okay? And what does this look like? Okay? Look at this. That right there is this, the antiderivative of the first function minus the antiderivative of the second function. So if we back it up, and we can do this, if we back it up and say, hey, these two functions, I am going to subtract them and take the antiderivative of the difference between the two functions, I should get the same answer. Now, having said that, the two things that you have to make sure that the upper function, okay, the upper function is f of x1. So you always have to take the greater function, or the function that has the graph above the other one. That one has to be first. And the graph beneath has to be f of x2. If this is the case throughout the entire interval from a to b, if they never cross over each other, then this will work. Okay? Then you can do this. You can actually take the differences of the functions themselves and then find the antiderivative of that. So as we can just continue on this one here, we are going to evaluate this antiderivative, okay, from 3 back to 1. And it's going to, again, it's going to look like this, isn't it? It's going to be 1/3 3 cubed. All right, and let's just go with this one right here. Minus 1/2 3 squared plus 3. And we're going to subtract from that this 1/3 1 cubed minus 1/2 1 squared plus 1. Okay, so you plug in your values, you get this right here. Come to a common denominator here, multiply all this times 3 and this times 3. What do you get? You get 45 over 6 minus 5 over 6, which is 40 over 6, reduces to 20 over 3. So as far as an area goes, that's the exact same area as when you did them separately. Okay, and we could do this a number of times. With this situation where both functions are positive, right? We kind of had this right here, right? Both functions are positive functions, which we know that this works for, this whole antiderivative area situation. And if this f of x1 is always above f of x2 over the interval that we're concerned about, we have a pattern here that we can call a rule. So let's just get to that. The summary that I would give you would be this: the area between the two positive functions, so obviously these functions are both above the x-axis for this type of situation, and they're both positive from a to b, okay? That area in between the two is given by taking the antiderivative of the positive difference of the two functions. So you can subtract f of x1 minus f of x2, and you get a difference as long as you take the function with the greater values as the first function, the function with the lesser values as the second one. And you can evaluate the area under that curve, that resultant curve. That would be the area in between the two. And I guess I would show you this function. Now, I did the example that we just got finished. I actually just did this on my graphing calculator, and I just kind of took a clip of this for you for class. But what I want to show you is this. This right here, this function right here, okay, this is the x squared plus 1. And this is y equals x. Okay, that's this one. and this is y equals